Hello, everybody. Welcome back to Math Force 9. We are today going to start talking about algebras. This is the last of the large topics that we are going to discuss this semester. We'll look at various different types. We'll look at different settings in which they arise and some of their properties. All right. Now, before we get into it, let's have a look back at the hierarchy of algebraic structures that you've seen so far. In Math 370, you first encounter what are called groups. Groups are basically the most elementary of nice algebraic structures. There are some other things called monoids and loops and things like this that are not so nice. But groups are a set equipped with a single operation. It's an associative operation. There's an identity element, and everything has an inverse. So they're really quite nicely well contained. Beginning of this semester, we started talking about rings. Rings are somewhat more natural than groups in the sense that most of the structures that you have seen to date before you get into higher level math are rings. All right, most of the sets we deal with have two operations. We defined a ring to be very, very general. It'll be an abelian group under addition. We require that multiplication be associative and that you've got these distributive laws to ensure that you can get a coherence between the two operations. Whenever the two get mixed, you have a way to, mix them. That's the very most general definition of a ring. We saw that you can get many different flavors of rings by requiring different properties. You can throw commutativity on. Most commonly, rings have an identity added because when you don't have an identity, it's kind of weird. You also saw in a homework exercise that if you have a ring that doesn't have an identity, you can embed it into a larger ring that does have an identity. We also saw integral domains. This gets rid of zero divisors. So when a times b is equal to 0, we know one of a or b is 0. That's a very powerful fact that you need when you're trying to solve equations. And then at the very top, we've seen fields. Okay. These are, in some sense, the most robust structure in algebra because you've got both of your operations. It's going to be an abelian group under addition, and with the exception of 0, it's going to form an abelian group under multiplication, and you've got all of your ring properties as well. Everything's got inverses. You don't have to worry about zero divisors. So fields, in some sense, are really very nice, and they are the natural setting in which to perform most of our day-to-day arithmetic. All right, but let's look at that also from the perspective of equations, okay? Because it's hard to believe with everything that we've been doing, but equations are what drive a lot of algebra, especially historically. So groups, one of the reasons that we like them is that they are the fundamental structure that's going to allow you to have a basic linear or affine equation, i.e. ax is equal to b. All right. Not only does that make sense, I mean, you need an operation in order to talk about multiplication. And the great thing about a group, though, is that its properties are precisely the ones that ensure such an equation has a unique solution. And in fact, you can sort of go in the reverse. If you have a structure in which this equation and its left-hand version, xa equals b, is well-defined and has a unique solution, it turns out it has to be a group. All right. Now, on the other hand, groups only have one operation. You can only deal with that one thing. So you can either have a multiplicative equation or an additive equation. You can't mix the two. Rings, that's why we like rings. Rings allow for the idea of a polynomial equation, okay? You can now mix multiplication and addition and set things up. The problem with rings is that if you have a polynomial equation in a ring, unlike a group, number one, it may not be solvable. All right, you can make up polynomial equations in rings that just don't solve. All right, the other thing is that if you can solve it, one of the great things about a group, that solution is unique. In a ring, that's not true. All right, now that's in general not true for polynomial equations. Polynomial equations are designed to have more than one solution, but in a ring, it can get worse. You can have infinitely many solutions to a single polynomial. That's sometimes useful, it's mostly not. All right, which again brings us back to fields. All right, that's why we like fields. I can talk about a polynomial of degree n in a field, all right, and it will have up to n solutions counting multiplicity. All right, so if you look at x squared equals 0, 0 is a solution to that. It actually has two solutions because it's x times x equals 0, so you count 0 twice as a solution. All right, we've also seen that with fields, if I have a polynomial equation and my original field doesn't have a solution, that's okay. I can find one that does. I can extend it using the Kronecker extension theorem and get a new solution. All right, now let's look forward. Where do we go from here? All right, there are several directions you can go in algebra at this point. One is to continue along the equation route. You can look at Galois theory. So the Kronecker extension theorem guarantees that you can find a solution, but it's completely non-constructive. So Galois theory deals with a specific case of looking at polynomials. You want to find a zero of it, and when can you find a solution to that in terms of radicals of the coefficients? Think about your quadratic formula. All right, if you look at ax squared plus bx plus c equals 0, you can find a solution to that in terms of a, b, and c, the coefficients. You have to add, multiply, divide by them, and you also have to take a square root. So Galois theory looks at when can you solve polynomial equations more generally using that kind of method. Some polynomials solve nicely, some polynomials don't, and Galois theory will tell you which ones are which. It is a wonderful piece of algebra, and if we were in class in person, I would consider it. It pulls a lot of what you've seen together. It uses a lot of stuff from fields, it uses a lot of stuff from groups. But I don't think that's a great way to go right now. So another option to look at is what's called module theory. All right. So very roughly speaking, modules are sort of ring analogs to vector spaces. Vector spaces exist over fields. All right. Modules exist over rings. So rather than taking your coefficients or your scalars from a field, you're going to take them from a ring. So this is a very broad part of algebra, particularly in commutative algebra and what's called algebraic geometry. If you go on to grad school, you will see a fair bit of module theory. It will make you understand just how wonderful a basis is in a vector space, because in modules you don't have them necessarily, and you will miss them a lot. Both of these are very interesting. If you go on to grad school, you will definitely see some Galois theory there as well. But what we're going to do is we're going to continue on that hierarchy. Okay, so you start with groups, you go up to rings, you go up to fields. What comes next? What comes next is what's called an algebra. All right, now, algebras are very broadly defined, as we shall see, much like rings. Very, very basically, you could say that an algebra is a vector space that's also got a multiplication on it. So there's a way to multiply vectors. So we tell you in back in linear algebra, you can only add vectors. You can't multiply them. Well, we can. We just don't tell you how. So we're going to see some interesting examples of that. We'll talk about some very basic examples today, and then start looking at some classes of them in future lectures. Okay, so before we launch into the definition, let's look at an example of an algebra that you've actually already seen. All right, and in some sense, it's actually a canonical version. Basically, n by n matrices over a field K. All right, so you've seen these in various classes. You've seen them in my class. You've seen them in your linear algebra class. All right, we've looked at them in Math 470 as a ring. Okay, I have two operations. I can add and multiply, and what does this mean? All right, you can also look at them as a vector space. They are a vector space over K. They have a basis in those matrix units. All right, but we started to look at some of the interaction between those things when we looked at how you multiply matrix units together. So they're the basis, but how do they multiply? All right, whereas in linear algebra, when do you really care about matrix multiplication? Well, there's one place where it comes up, composition of linear operators. If I have one linear operator being represented by a matrix and I have another one being represented by a matrix, if I want to compose them, I multiply the two matrices. And when else do you run into it? Not very often. All right. You use it in some of the fancier decompositions of matrices. If you look at singular values, you look at the LU factorization for solving equations. If you've seen the Jordan normal form, sometimes you run into it there. You run into it with change of basis, but that's about it. And all of those focus on a single matrix. All right, you're finding the singular values of a matrix. You are finding the LU factorization of a matrix. You are changing the basis for a matrix. We want to look at what happens more generally to the entire algebra, to the entire set of matrices when you start mixing the fact that you have a basis with the multiplication. All right, so let's start with the definition. Okay, so an algebra over a field K, it's going to be a quadruple. You're going to have this non-empty set A paired with or joined with three operations. All right. One of those will be addition. All right. This will be a binary operation on A. One will be multiplication. So again, another binary operation on A. So I can add two vectors. I can multiply two vectors. And then there's going to be a scalar multiplication. So I'm going to work with my field K elements from the algebra, and I can multiply any element by a scalar. And it's going to satisfy following. As talked about, this is going to be a vector space over K. So K will form the scalars. I have addition of vectors, and I have scalar multiplication. Part of that, keep in mind, that means that under addition, it's going to be an abelian group. All right. On top of that, we require that the distributive laws hold. Okay, so if I have, for the multiplication, I have three vectors, I can distribute on the left and I can distribute on the right. And we also require that scalar multiplication be so-called central and associative. So scalars will commute with vectors. All right, and I can pair them up any way I see fit. Okay, now, this is our definition. So I have my three operations. But if you look at it, there's something missing from that definition. Something that we usually see in a lot of our definitions of algebraic structures. So, what's missing? I'll give you a chance to think about it for a sec. Okay, so what's missing? We don't require that multiplication be associative. This is a first, okay? All of our operations to date, we have required that they be associative in some way, shape, or form. All right? For algebras, we drop that requirement. All right. Now, just as with groups, even more so with rings, even more so with algebras, there are hordes of different types. Okay, so while we do not require associative, it could be. Okay, you could have an associative algebra. Matrices are an example of that. Multiplication there is associative. All right, but we also have what are called non-associative rings, or sorry, non-associative algebras, where we don't require the multiplication to be necessarily associative. It could be, it doesn't have to be. Parts of it may be. All right, so there might be large portions of the algebra where the multiplication works associatively and large portions where it doesn't. Okay, we can talk about commutativity versus non-commutative. All right, there will be commutative algebras and there will be non-commutative algebras. Again, case in point, matrices. Matrices are a non-commutative algebra. On the other hand, you can think of fields, extension fields as algebras. Those would be commutative. We will talk about unital algebras, algebras that possess an identity element. Again, there's not a requirement that it does, but as with the ring case, if you're in an associative case, you can sort of force it into one that does have an identity, but it's not a requirement. All right, the other thing is dimensionality. So it could be a finite dimensional vector space. All right, if it's infinite dimensional, can you guess what that means? All right, most of the vector spaces that you've dealt with have been finite dimensional. We will see that when you start forcing that multiplication on the vectors, finite dimensions may or may not be convenient. There are going to be times when you want it to be infinite dimensional. When you're working with vector spaces on their own, you usually don't want that if you can avoid it. Sometimes you can't, sometimes you can. Now, one of the things I just want to mention in passing, associativity and commutativity are independent. Okay, you can have non-associative, non-commutative algebras. You can have a commutative algebra that is non-associative. You can have an associative algebra that is non-commutative, and you can have something that is simultaneously associative and commutative. All of those things just work independently of each other. One doesn't force the other in any way, shape, or form. We will see that in the coming lectures. Okay, so let's look at our first example. Good old n by n matrices. Our operations are what we know and love: standard addition, standard matrix multiplication, and scalar multiplication of matrices. As mentioned, it's an associative algebra, which is nice for your first example. It is non-commutative, very highly non-commutative. You've seen that the center is just the scalar multiples of the identity. Speaking of which, it is unital. It has an identity, namely the n by n identity matrix. And it's nice and finite dimensional. It's got a basis E sub ij, where E sub ij is that matrix unit with a 1 in the ij position and zeros elsewhere. There are n squared of those, so it's a nice finite dimensional algebra. All right, for our next example, you'll notice it's example 1.5, and you'll see why in a moment. We're going to take a vector space V, and we're going to take what are called the endomorphisms of V. So the endomorphisms are the set of all... Oh, wait, there's a small typo there. Hold on, let me fix that. Okay, there, that's fixed. All right, so the ring of endomorphisms, or the algebra of endomorphisms, this is the set of all linear maps of the vector space back onto itself. So, operations, it's going to consist of function addition, function composition for our multiplication, and then standard scalar multiplication. I just take lambda and I multiply it by my scalar alpha. All right. Is it associative? Most definitely. Function composition, no matter where you're setting the whole thing, no matter what you're working on, function composition is always associative. Is it commutative? Yeah, not even close. We'll see why in a moment. Is it unital? Yes. You take the identity map. You take id v of v is just v. It just returns the vector back. All right. Now, is it finite dimensional? Well, this is why it's example 1.5, not example 2. If v is a finite dimensional vector space, then yes. If I take a basis v1 through vn of v, I define these linear functions lambda sub ij on vector vk. It will take vk and map it to vj if k is equal to I. All right. Or it will kill it otherwise. This forms a basis. It's not too hard to check. I will probably make that a homework exercise. And therefore, it's going to have a dimension of n squared. All right. So what that actually means when you think about it is that if I have an n-dimensional space, then the endomorphism algebra is actually isomorphic to the n by n matrices. Now, if V is infinite dimensional, though, NV is massive. Okay, V will be of one infinite dimension, NV will be of a larger one. Think countable versus uncountable. All right, but when it is finite dimensional, it's just your matrices kind of in disguise. All right, example 2, we'll take the polynomial algebra. Now, we've talked about polynomial rings. Well, they are actually an algebra. All right, so my operations, again, polynomial addition and polynomial multiplication, but for a scalar multiplication, if you think about it, I could take a constant polynomial and I could just distribute it across a polynomial. So that gives me my scalar multiplication. All right, whoops. It will be associative. K is commutative. The way we set this whole thing up, K adjoined X will be commutative. It's unital. We use the unit from K. But it's infinite dimensional because I can take arbitrarily high powers of X. And the powers of X, 1x, x squared, x to the n, etc., they are going to form the basis. So that will be an infinite dimensional algebra. For our next example, let's look at something that's a little more concrete. Let's look at the quaternions, and these are going to form an algebra over the real numbers. All right, so we've seen this, you've seen this plenty of times by now. Your addition is component-wise. The multiplication is defined using the relationships between ij and k, and you force it to be distributive. And then as for scalar multiplication, I can just distribute any real number over any quaternion. It is definitely associative. It's a nasty little computation, but it works. It is also definitely non-commutative. All right, I times j is k, but j times I is negative k. It's unital. I've got one inside there. And it's nice and finite dimensional, and in fact, it's four-dimensional. It has a basis consisting of 1, I, j, and k. So again, another algebra that you've seen. We haven't really identified it as such, but it is. Okay, so far I've been showing you examples of things that you've already seen. And many cases it's been a ring. We haven't stressed the fact that it's an algebra. So you might be wondering, well, why do we bother? All right, so let's have a look at one you haven't seen before. All right, so I've told you the story of how quaternions were sort of discovered, invented, created, however you wish to describe it, where Hamilton had been trying to figure out how to multiply triples together and then realized he had to go with quadruples. He communicated this to another mathematician by the name of Cayley. And Cayley sort of thought, well, why stop there? So there is a structure called the octonions, or sometimes called Cayley numbers in honor of Cayley, and it is an R algebra. So R forms the scalars. All right. It has a real part and then 7 imaginary parts. All right. So it has a basis consisting of 1 and then these 7 objects E sub I. So everything is an 8-length sum. Now, how do you multiply them? Very, very carefully. We work out how to multiply EI and EJ, and then you're going to extend it using distributivity, just like we did with the quaternions. So we need a 7 by 7 multiplication table for the E sub i's, and there it is. All right. So, and there is a small typo. Let me fix that quickly. Okay, there we go. Now it's fixed. Okay, so this tells me how to multiply any E sub I by any E sub j. Note in particular that if you take any one of these E sub 1 through E sub 7 and you square it, you get -1, just like you do with the quaternions. All right. On the other hand, this thing is kind of a mess. All right. So how do we do it? Well, operations, okay, it's going to mimic a lot of what we saw with the quaternions. It's going to be component-wise addition. All right, so I've got 8 dimensions. I add each one to itself. All right, multiplication, again, you use that table and you expand it using distributive property, and then you assume that constants, i.e. the real numbers, will distribute across any of the E sub i's. Now, this thing is non-associative. All right. Very quick example, if I take just E1, E2, E3, if I take E1 by E2 and then by E3, I get negative E6. And if you take E2, E3 first, multiplied by E1, you get E6. So they differ by a negative. But that's enough. It means it's non-associative. Now, on the basis elements, the non-associativity isn't too bad. Usually reassociating like this will do exactly the same thing. It'll induce a negative. But when you take that across an 8-dimensional object, it becomes a mess. All right. It is also non-commutative. All right, same deal. If you take any E sub I and E sub j and you reverse them, you pick up a negative, just like you do with the basis of the quaternions. But then again, when you spread that across 8 dimensions, it becomes even worse in terms of the commutativity, or lack thereof. All right, it is indeed unital. It's got a unit, namely just the real number 1. And as I've been saying, it's 8-dimensional. It's going to be, the basis is 1 for the real part, and then E1 through E7. Okay. This thing is kind of messy, and you'd think, why would you ever do it? Sort of unbelievably, though, it plays a large role in realizing a lot of other algebras that are out there. We will look at a couple of its properties probably in the exercises that I'm going to give you. I won't make you prove lots of things about it because, as I said, it's big and nasty. But there is a sort of an interesting thing that happens. So if you start with the real numbers, those are a 1-dimensional algebra. You can make the complex numbers. Those are a 2-dimensional algebra over R. Then you make the quaternions, which are a 4-dimensional algebra over R. And then you can make the octonions, which are an 8-dimensional algebra over R. So then the question becomes, can you keep going? Noticing that that dimension is doubling every time. You can. There is something called the Sidonians, which are a 16-dimensional thing. And notice I said thing. I didn't say algebra. Because the Sidonians are not well behaved. All right. If you look at these structures so far, R is a nice ordered field. C is still a field, but it's no longer ordered. You can't decide whether I is larger than 1 or less than 1. Okay, so everything's still invertible, but you lost something when you went from R to C. When you go C to H, you lose commutativity. We've shown that H is a division ring. Okay, so everything still inverts, but it's no longer commutative. You've lost something else. And then you go up to the octonions. It turns out that these will also have division ring properties. Things will be invertible, but you've lost commutativity and you've lost associativity. If you double it again, it just completely falls apart. You still get this structure, but it's now non-commutative, non-associative. It has problems that you can't always multiply everything together by other things. You get into closure issues of all things. And it sort of falls apart at that point. But it's a pretty cool process. And it's something that we might look at towards the end of the semester. It's something called the Cayley-Dixon process. All right, so that should give you an overview of some different types of algebras. We're going to start next lecture by looking at some common associative algebras. I'm going to look at least 2 of them with you. We might look at a third. The third one's not particularly interesting. The first one is called the tensor algebra, which is a somewhat complicated structure when you first see it, but it is remarkably useful. We can use it to construct just about any other algebraic structure we want if we're careful. Okay, but those next 2 or 3 are all going to have the same common thread. You're going to start with a vector space, and we're going to take that vector space and construct some algebras on it. And then we will see some interesting properties from there, and we'll actually see some things that you've seen in linear algebra will fall out very quickly by using the algebra structure rather than having to build it up from scratch. Okay, so until next time, have fun.